YouTube traffic, this is 345 Delta Foxtrot, ready to record another YouTube video. YouTube traffic. This is my disclaimer. If you haven't already seen it, please take a few seconds to take a look at it. Okay, this is part 2 of my videos on aluminum alloys. If you haven't seen part 1, please watch that first. I think this video will make a lot more sense to you, be much clearer if you've already watched part 1. And of course, I'll put a link to part 1 in the description. Okay, in part 1, we saw that the 2024-T3 aluminum alloy has significantly better, stronger mechanical properties than pure aluminum, the 1100-O aluminum alloy, for example. And this is due to the addition of a few percent copper, about 4% copper, 1.5% magnesium, and about 0.5% of manganese. And it is also due to the T3 heat treatment. However, not everything got better. As the alloy got harder, it also got more brittle. And also the corrosion resistance got worse. So we need to talk about those two things. Okay, first let's talk about the aluminum getting more brittle and how that affects bending aluminum. Okay, this is a table of the minimum bend radius for various aluminum alloys, and it's taken from the Aviation Maintenance Technician Handbook, Airframe, page 4-61. And let's just pick a thickness, an arbitrary thickness, let's say 40 thousandths. Okay, you see that for the alloys on the left side of the table, they're all basically -O's. They're basically just annealed, and they're probably fairly pure aluminum. And they have a fairly small minimum bend radius, 0.06 inches. If you look at the 2024, it is 0.16 inches. So the bend radius has gotten significantly larger. And if you keep on going and you look at, say, the last column here, the 707 alloy, which is either the hardest of the aluminum alloys or close to it, it has an even larger bend radius. Now we're up to about 0.22 inches. It's almost a quarter of an inch. You need to be careful about trying to put a very nice, sharp 90-degree bend in your aluminum. You actually don't want to do that. You want a little bit of a rounded bend. There's several other videos about bending aluminum on YouTube, and you can take a look at them if you want. The basic problem is most of us don't have the equipment to put a precise a bend with a precise radius when we're trying to bend aluminum. Say you wanted a bend radius of 1/8 of an inch. Well, how are you going to do that? You could take a 1/4 inch rod and try and bend it around that, and you might work okay. But you really don't have the equipment for doing it bends in a nice controlled way. At least I don't. So you take a more practical approach, and You just take a look at what Vans does. Take a look at a rib or something where the edges are bent at 90-degree angles, and you try and bend things approximately the same way. And you certainly don't go out of your way to make a super sharp 90-degree bend. That is not a good thing to do. Okay, now we need to talk a little bit about corrosion resistance. Now, aluminum is much better than steel. Actually, there's some pretty good stainless steels, but like the low and medium carbon steels, and the high carbon steels, they rust pretty readily. So aluminum is way better than they are. And the reason for this is aluminum forms a very high quality oxide. Um, when fresh aluminum is exposed to the air, it oxidizes very quickly, like within seconds or minutes, and it forms a thin oxide layer, and that's Al2O3, which in chunks is called sapphire. If it has a little chromium in it, it turns red, and it's called a ruby. And if it's green, it's called an emerald. But it is a very durable, very hard oxide layer. And this oxide layer can block any water from the surface of the aluminum. Now, it turns out pure water is not a problem. Pure water does not corrode aluminum. Pure water is H2O, and the hydrogen is not going to do anything. And all the oxygen is going to do is increase the thickness of the oxide layer, which is protecting the surface. But what corrodes aluminum is chlorine ions. However, there's not many chlorine ions just floating around in the air. Where you find chlorine ions is in saltwater. And so that's why you want to protect the aluminum from water. You want to protect it from water that has any chlorine ions in it. Okay, so pure aluminum actually has pretty good corrosion resistance, but the 2024-T3 alloy does not have very good corrosion resistance. One paper I saw on a scale of A to F, they gave the 2024 aluminum a rating of F for, I'm sorry, a rating of D for corrosion resistance. So why is that? What is the copper doing? And obviously the copper is messing things up somehow, and perhaps a little bit the magnesium and the manganese, but probably the copper. I tried to look that up, and there's one paper, the reference is given here. This is what they had to say about it, and as far as I can tell, it's just a lot of fancy words saying that the alloying elements mess things up. Wasn't really very helpful. But we can speculate a little bit on what might be going on. And just remember that this is just speculation on my part, and I can't really back it up with scientific data. We know that it's not just the copper, it's the copper near the surface. If you put a thin layer of pure aluminum on the surface, that will actually protect the material from corrosion. And in fact, this is what Vans uses. Their 2024 aluminum that they use for their skins has a very thin layer of pure aluminum on the surface to protect it from corrosion. This is not something that Vans does. They buy it from a very large aluminum manufacturer. and the manufacturer is the one that actually puts the aluminum cladding on the surface. But the aluminum cladding is very thin, and so we know that just a very thin layer, if you keep the copper away from the surface just a little bit, probably just a few microns, then it doesn't mess things up in terms of the corrosion resistance of your piece of metal. So if you have a few atoms, a little copper precipitate sitting on the surface or very, very near the surface of your alloy, presumably the copper oxide is not nearly as good as the aluminum oxide. It provides a little hole that some chlorine ions can get in, and they start corroding the aluminum right underneath and right near the copper precipitate. And once it starts, it just continues. It just propagates. The little pit just grows both vertically and horizontally, and gets worse and worse. So that's my theory anyway about what's going on. Okay, I just mentioned the fact that Vans uses the thin layer of pure aluminum on the surface of their skins to provide corrosion protection. Another good way to provide corrosion protection is to use primer. This is just a paint type primer. You want to use a high quality one, of course, one that's designed for this type of application. Now, the problem is that primer does not stick very well to the aluminum oxide, to the Al2O3. So you have to prep the surface to get the primer to stick, and typically you use an acidic prep. And when I do the acidic prep that I do, the appearance of the surface changes noticeably. And I believe that it's basically removing all of the pure aluminum cladding. So basically, what you're doing is you're removing one layer of corrosion protection, the pure aluminum cladding, and you're adding another layer of corrosion protection, which is the primer. Now, hopefully, the primer is very effective, and it's a good thing to do. However, I don't know of anybody that's actually done the experiment. If you just take, say, 3 pieces of metal, one that's just straight 2024 aluminum, one that's the 2024 with the cladding, and one that has been primed, and you set them out in the air for months or a year or whatever, what happens? And I don't know the answer to that. I do know that for their quick build kits, Vans does use a spray primer. And we also know that they had some problems with it. They had some problems with the primer that was being used on their quick build wing kits in Asia. And when they shipped them from Asia across the Pacific Ocean, they corroded and had to be thrown away. So presumably, it's Vans's opinion that spray primer is better for corrosion resistance than just this thin layer of aluminum cladding, or they wouldn't go to the trouble of spray priming these quick build parts. Okay, we've talked about the basic mechanical properties of the aluminum alloys. However, there's some other properties as well. So let's talk about those. Okay, the melting point of aluminum is about 570. The melting point of steel is almost 3 times higher than that in degrees centigrade. It's up around 1400 degrees centigrade. So steel wins big time there. And the coefficient of thermal expansion of aluminum is somewhat higher than it is for steel or brass. The specific heat capacity and the thermal conductivity are given in the table here, but I don't know how either of those would be applicable to building an airplane. So I'm just going to kind of skip those. The electrical resistivity of aluminum is very good, especially compared to steel. The only thing that you have to be careful about is this high quality oxide that forms on the surface, and that Al2O3 oxide layer is a very good insulator. So you need to be very careful about making aluminum to aluminum electrical connections. That's one of the primary reasons I think that aluminum wiring is not used in houses. Also, aluminum is hard to solder. That's another reason why copper is used over aluminum in most electrical applications. The machinability of 2024 is listed as good, and I don't really have anything more to say about it than that. And the corrosion resistance is poor, which we've already talked about. Okay, so in terms of the melting point, as I already said, the steel is way higher than aluminum. Now, there's no danger of your airframe melting, but it can heat up. And 100 degrees C is a big deal for aluminum because the melting point is so low, whereas 100 degrees C is a drop in the bucket for steel. It's not really going to affect the mechanical properties of steel at all. But the aluminum will start getting softer at well below its melting point. So something that you definitely want to be careful about, especially in the areas of the plane that have higher temperatures, like the engine areas, the exhaust areas, anything that's forward of the firewall. Okay, the coefficient of thermal expansion is the amount that a bar of aluminum of some given length will, the length will change with a given change in temperature. The formula is given here. The change in length divided by the length and divided by the change in temperature is the coefficient of thermal expansion. And for 2024 aluminum, it's 23 microns per meter per degree C. We can just stick some numbers in the formula real quick and see what we get. Let's assume a change in temperature of 70 degrees C, and that's 126 Fahrenheit. And that's something that an airframe could easily see. You have winter at high altitude on the low temperature side, and you have Phoenix in the summer on the high temperature side. And the difference could easily be 126 degrees Fahrenheit. Um, you could have a piece of aluminum, on the order of 2 meters in an airframe. So that's the number I used. Um, so you calculate the change in length for that length and change in temperature, and you get 3.2 millimeters, which is not a lot, but it's not totally insignificant either. Now, for aluminum to aluminum bonding, it's not a problem. If one layer expands, the other layer is going to expand, and if one layer contracts, the other layer is going to contract. But if you have a layer of aluminum and a layer of composite, uh, and they're bonded together, and the aluminum expands by 3.2 millimeters, and the fiberglass or the composite material only expands by 1 millimeter. The material, if this is the aluminum and this is the fiberglass, is going to curve in that direction. The aluminum is going to expand more than the fiberglass, and it's going to bow or bend significantly. This is how bimetal thermometers are built. Um, so you want to be careful of any cases like that. Okay, now I want to talk about a few miscellaneous topics related to aluminum alloys, rivets, lightning holes, and laser cut parts. Okay, we talked about what the skins are made out of. They're made out of 2024 T3 alloy. But what are the rivets made out of? Well, the most common rivet for the skins of an RV is an AN 426 AD 3-3.5. So the AN stands for Army Navy, the 426 stands for the head shape, and 426 means countersunk head, as you can see in the pictures to the left there. The AD is the alloy code, and the AD alloy code is for 2117 aluminum. So it's also in the 2 series. So the primary impurity is copper, and just the A alloy code is for 1100 aluminum, or basically pure aluminum. And the way those are distinguished in rivets is the AD rivets have a dimple in the top of the rivet, whereas the pure aluminum rivets just have a flat, flush head at the top. So you want to be very careful and make sure that all of your rivets have a dimple. Well, all of your rivets that are used in any sort of structural application. If you're riveting an ashtray inside the cabin, probably doesn't matter what kind of rivet you use. But for anything structural, make absolutely certain that you're using rivets with a dimple. Then the 3-3.5, the 3 is the diameter in 30/2 of an inch, and the 3.5 is the length of the rivet in 1/16 of an inch. And again, this is from the Aviation Maintenance Technician Handbook, Airframe, page 4-33. And this is the FAA publication that I recommended that you get familiar with. So this is your second reminder to get familiar with it. Okay, I have been kind of curious about lightning holes. Does it really make sense to punch great big holes in the parts of your airframe? Now, certainly it will make them lighter. Now, maybe I should make it clear that when we say lightning holes, we're talking about lightning as in making something way less, not lightning as in a thunderstorm. So we're talking about making these big holes, in this case a wing rib, in order to make it a little bit lighter. And does that make sense or not? So we can do a quick calculation. I took that particular wing rib and I weighed it, and it weighed 170 grams. It has two lightning holes. One has a radius of 6.4 centimeters and one has a radius of 4.5 centimeters. The thickness was 0.086 centimeters or 0.8 millimeters. So you can do a quick calculation and you find that the mass of the aluminum that was cut out of those holes was 46 grams. So the piece before the holes were cut weighed 170 plus 46 grams, which is 216 grams. And you just take the ratio of after divided by 4, 170 divided by 216, and that's 0.79. So basically, by cutting those lightning holes in that rib, there was a 21% weight savings. And, that's quite significant. One thing that you want to be careful about is, that's the percent weight savings for one rib. What is the total weight savings? If it were just the one rib that you were putting these lightning holes in, it wouldn't be worth doing. You would only be saving 46 grams, that's the less than the weight of the change in your pocket or something. So assume that there were 100 similar parts in your airframe, and each one there's a weight savings of 46 grams. So that's a total weight savings of 4.6 kilograms, and that's just a little over 10 pounds. And again, that's pretty significant. That's a little less than the weight of 2 gallons of gasoline. But like I said, it's definitely significant. You have two basic options for a part with a fixed weight. You can either go with a thicker aluminum and lightning holes, or you can go with a thinner aluminum and no lightning holes. And I would be very curious to know what the strength difference between those two cases is. Obviously, Vans thinks that it's better to go with the thicker aluminum and the lightning holes. But I think it would be very interesting to actually see some data on that and how much, what the trade-off here really is. Okay, in addition to the two lightning holes that you can see in this picture, you can also see a horizontal indentation between the two lightning holes. And then at the top, you can see kind of an upside down T-shape set of indentations. And I believe that these indentations make the rib stiffer. And also, you can see there's indentations around the lightning holes. And I think if it weren't for those indentations, I mean, if you were to just cut big holes in the rib, I'm not sure it would be structurally sound. But since you are also putting these indentations around the edge of the lightning holes. I think that adds back a lot of the stiffness that you lost by cutting the hole. Maybe even adds more than stiffness than you had in the first place. Okay, the last little miscellaneous topic we have is laser cut parts. And the laser, to cut the parts, not only does it have to melt the aluminum, it basically has to vaporize it. And the boiling point for aluminum is 2470 degrees C, so it is very high. So you have to wonder how much did the laser change the temperature in the aluminum near the cut. Now, what it has going for it is it was all done very quickly. It was heated up and vaporized very quickly, and it was cooled down very quickly. So hopefully the copper atoms in the nearby aluminum did not have time to move around, and the aluminum grains near the cut did not have time to recrystallize and grow. Now, you don't know for sure until you actually do fatigue testing on something like that. At least I certainly don't know for sure. You can speculate that it was done so quickly that it doesn't matter, but it really needs to be tested before you actually start using parts like that. And I will try and make a separate video about laser cut parts, and we'll talk about it more in that video. Okay, that's it for this video. That's it for aluminum alloys. If you want to recommend these videos to other people, please subscribe, give it a thumbs up, or leave a comment. Any of those three will tell the YouTube algorithm to start recommending these videos to other people with similar interests. Now, in these last two videos about aluminum alloys, we've finally gotten to some topics with some technical meat. The question is it too much meat? Is it not enough meat? Or is it about right? So if you've watched these two videos, please comment on that and what you think about the amount of technical meat in these last two videos. So, thanks for watching.